Thank you. So welcome, Veronika Pillwein. So she'll be talking on the positivity of holonomic sequences.
Thank you, and thanks for staying up so late in different parts of the world. Yeah, I'm talking today about positivity of holonomic sequences. I want to start out saying what is holonomic. And by the way, if there's any question, please feel free to interrupt anytime. Yeah, so holonomic sequences, I call a sequence holonomic if it satisfies a linear recurrence with polynomial coefficients. And we saw a very similar definition in Lewis' talk about C finite. So other names for holonomic are also P finite or P recursive for polynomial coefficients. And my first example for holonomic sequences actually are the Fibonacci numbers again. So we have seen this recurrence. So these are C finite. This is a special case of P finite. The factorials that Lewis showed, they are the recurrences of this type also. So they are P finite. Or the harmonic numbers also, for instance, they satisfy this recurrence relation. And another example, Legendre polynomials, they are also P finite. So here now the coefficients, I also have a dependence on this continuous parameter x here. And I'm showing Legendre polynomials because most of the inequalities that I show today will be related to orthogonal polynomials, or in particular Legendre polynomials. So Legendre polynomials are the polynomials defined that are L2 orthogonal on the interval 1. So the integral of Pn times Pm is 0 unless n is equal to m. And Legendre polynomials satisfies, you see, a recurrence of order 2. This is true for all orthogonal polynomials. Satisfy a linear recurrence of this type where the x only appears here, and 3-term or second order. Okay, so this is this, and I will start out. So I want to talk today about inequalities. So you have seen maybe Antonio's talk. He talked about closure properties for DD finite functions. So holonomic sequences satisfy many closure properties, like adding two holonomic sequences are holonomic again, or multiplying, or also summing holonomic sequences. And there's a lot of algorithms for identities involving holonomic sequences, but not so much for inequalities, which is the topic today. And I start with a very classical inequality on Legendre polynomials, namely Turin's inequality. So we have this determinant here that Pn squared minus Pn minus 1 times Pn plus 1 is greater equals 0. And here I plotted a few of these values, this delta 4, 6, and 8. And you can see, so at minus 1 and 1, they are exactly 0. Then if you go beyond, it becomes negative. So this is really in minus 1, 1. And Legendre polynomials, they have they only have simple roots within the interval minus 1, 1. So as you can imagine they're oscillating a lot. And if you look at this Turin determinant, this looks very smooth compared with all these oscillations are somehow gone. They are from 1 degree to the next, they're not monotonically increasing, but decreasing. The other way around could be nice to use for a proof. And in fact, with the right scaling, it has been used for a proof also. So these are the, yeah, they were, as far as I know, this inequality was introduced by Turin in a paper in 1950, but he must have circulated this before, because in 1948, Segel gave 4 different proofs of this inequality. So this is quite some time ago. And still people look at this problem and this type of problems. So let me give a brief idea of one of the 4 proofs that Segel gave. The first proof. So here we see the records again that I had in the first slide, just shifted and rewritten a bit. And he finds that using this recurrence, he can write this Turin determinant in this form, as this quadratic form. That is easy to show that this is positive provided the x is in this range. And this number here, if you plug in the n for different values, is something that is already close to 1 and is tending to 1 as n goes to infinity. So this shows the inequality for most part of the interval. And for the remaining part, he uses this Mehler's formula, and then from there it continues with some estimates. In the end, a simple argument, but yeah, so it works then also to fill the gap at the side. Why am I showing this proof? There are 3 others, because this is in the spirit that of the proofs and the approaches that I want to talk about today, that I'm trying to prove an inequality and using only the recurrence as a knowledge somehow. So this is the representation. So the first part of the proof is kind of where I'm going to. And the method that I'm following is something that 2 colleagues at Linz have developed now, like 15 years ago, I think. So Gerhold and Kauers, and it's a symbolic method that is applicable to inequalities that involve expressions satisfying recurrences along a discrete parameter. And this works for rather general recurrences, so not only holonomic, so linear ones, but also non-linear ones. They have to satisfy, of course, certain conditions that you can actually compute the things from these recurrences. But this idea works for more general recurrences that we see today, that I showed today. The basic proof idea, and we will look at an example in a moment, proceeds by induction along this discrete parameter. And in the end, it uses cylindrical algebraic decomposition, so quantifier elimination. And this is also part of the reason why this method is computationally very expensive. This lies within here. And something that was a topic also at the end of the previous talk. So this is a method, this is not an algorithm. Termination cannot be guaranteed a priori in general. There's a mathematical implementation of the method. This was written by Manuel Kauers in his package SumCracker. This is available on his web page, for instance. And so SumCracker already indicates that inequalities is not the main part. There are also things related to sums and recurrences and so on and so forth. Good. So let me give you an idea how the method works with a simple example. So let's look at something that is p finite of order 2, so satisfied by this type of recurrence. And I talk about positivity, so I'm talking, say, about fn greater equals 0 or greater 0 or less than 0. I can think of everything in terms of more or less non-negativity or positivity. So let's say our goal is this recurrence, and we want to show that fn is greater equals 0 for all n. As I said, I want to do a proof by induction. So assuming that fn plus 1 is greater equals 0, they want to show that fn plus 2 is greater equals 0. And for this, they plug in the recurrence relation to express this. And okay, this may or may not work. This is part of the problem, that the proof by induction may not work for all problems, for all input. And then they take this input and they generalize it. So they replace fn by a real variable y0, fn plus 1 by a real variable y1, and the n by a real variable x. And then we write this right-hand side. So this is a more general statement. So if this general statement is true, then our induction proof goes through. But this later thing may be wrong, even if the original thing is right. The advantage is it can be proven automatically using CAD, or checked at least if it's true or not. So what I say here, but it may be false, even if the sequence is non-negative. And if this is not true, then what they try is to add this conclusion here to the assumptions and shift the conclusion by 1. So they extend the induction hypothesis, and here this is essentially the formula for saying that fn plus 3 is greater equals 0 expressed using the recurrence relation. And every time they extend the induction hypothesis, you check if the next initial value is really still greater equals 0, because if you find a counterexample, you have at least a proof that it's not greater equals 0. So this process of extending the induction hypothesis may go on forever and ever. So this is where this becomes not necessarily terminating. But if it works very nicely. So for instance, for this Turan inequality, it works. And this is now showing this package. So how you would use this package. So the command would be proof inequality. Here I'm cheating a bit. So you could, what you would write is Legendre P. So the way Mathematica understands Legendre polynomials, I'm writing it shorter so that it fits nicely on the slides. But you can use the Mathematica built-in name for it. And Manuel already included in his package that the basic special functions, he already provides the definition. So you don't have to give the recurrence of Legendre polynomials. But what you have to tell is these additional parameters, where they are supposed to be, because the inequality doesn't hold for all x. What is the variable? And this info level is something that will show some output that I showed now. So this is just an additional option. And in the what I said before, it would be now fn greater equals 0. So this would be the delta n. So the whole thing that I have defined here. And by closure properties, we know that this Turan determinant satisfies the recurrence. So it is of the right form for an input. But if you use this recurrence, this will not work. So this linear recurrence, so in the spirit of how I explained the method before, this will not terminate. Instead, what is really used is the approach that also Sego used. So you shift this thing and you use the recurrence for the Legendre polynomials. So here you would, Pn plus 1 would be replaced already by Pn and Pn minus 1, and everything shifted will apply this Legendre recurrence. Okay, so the output then of this thing would look like this. So he's looking for the induction step. He is checking the initial value, extends the induction hypothesis, which I think in this step means just do it the first induction hypothesis. Checking, this is the CAD. It doesn't work, so he checks the initial value again, extends the induction hypothesis, checks the induction step, and here it says true. So then this thing works, so he had to extend the induction hypothesis 1 or 2 times, so depending on how this output works exactly internally. And this is something that could keep going on and on and on if you're unlucky somehow. But if you're lucky, like in this case, this works in a fraction of a second to get this result out. Okay, good. Let me just relate the result and talk a bit about this termination issue. So together with Manuel, I have looked into when does this thing terminate. And in these 2 papers, we consider recurrences. So in the first recurrences up to order 3, and the second 3, and some results above. And for recurrences that, first of all, they have, we in Lewis' talk, we saw this characteristic polynomial and eigenvalues. So in the corresponding thing for p-finite sequences with distinct eigenvalues with a unique dominant eigenvalue, and sequences that exhibit the asymptotic behavior that is dominated by this largest eigenvalue. So these are the theoretic assumptions, and then we can identify domains for these eigenvalues where the algorithm will provably terminate, and there are also some variations of the algorithm that is the termination. So this is what we found out on this method for terminating. There is, unrelated to this algorithm, there are other considerations by this group of people where I would say this Joel Orkney, James Worrell, and Florian Luca. These are I think driving forces, they have more results related to this. So this is analyzing positivity and minimality, in this case for second order holonomic sequences. And they are still ongoing, analyzing these things related to the Scholar problem also. So this is, if you're interested in inequalities, these are also probably fun to look at. This Turing inequality, this determinant is an squared minus an minus 1 times an plus 1. This greater equals 0. This is also locking concavity. And related to log concavity, there are a lot of particular results also by different people. And this by Jing-Hu Ho and Guo-Ji Li is very recent. And they also start only from the defining recurrence relation, but they look at when this log concavity holds asymptotically. So this is, they also have a method to prove this, and they have certain criteria. So this is only for a log concavity, but as I said, this is an interesting sub-problem that many people still look at. And then I want to mention two that are now not computer algebra at all, but this is classical analysis. This is Richard Schwartz. And he has, so I'm talking about this paper now. When I was preparing the slides, I realized he has a very recent one. So the latest update of the second paper is from June 21, so last month, on the archive version. And he is also, he's looking at these Turing determinants for orthogonal polynomials, characterizing it through the coefficients of the recurrence relation. And because this, so I showed the Turing determinant for Legendre polynomials, they hold for different other orthogonal polynomials. And typically, so for these results, the orthogonal polynomials are normalized to be 1 at x equal 1. So let me show one of these results of Schwartz. So I'm looking at the symmetric case. So he considers family of symmetric orthogonal polynomials defined on -1, 1. So we have this condition, and they satisfy a 3-term recurrence of this form. So for symmetric orthogonal, here the coefficient of Pn here is 0. So we rewrote here, we have the highest order. He takes this coefficient, the one that has the x, the coefficient to the left-hand side, and then we denote these coefficients by alpha n and gamma n. These initial conditions, they are common for orthogonal polynomials, so this is nothing special. And this condition here, that alpha n plus gamma n is equal to 1, this just says we are normalized to be 1 at 1. And the Legendre polynomials, they are of this type. So here we see this type of recurrence. And for instance, Jacobi polynomials would satisfy a recurrence of this type, but not with the 0 here. So this would be non-symmetric. And now I want to point out this alpha n. So this is this n over 2n minus, sorry, 2n plus 1 here. So, and his result says that if this alpha n is non-decreasing and bounded by 1/2 from above, then this Turing determinant is greater equals 0. So, and let me just go back. So here it's non-decreasing, and clearly it goes to 1/2. And his proof, this result is actually something that could be like a role model for Gerhold Kauers, because his result could be easily proven this using this technique. So we can do this translation that we did before. And now, as I said, we could do this for each of the components. So we could say this alpha n plus 1, we replace them by 2 real variables, the polynomials again by some real variables y0, y1. And then I can do an inductive proof where I have my induction hypothesis and my conclusion. And I add the range of the x, the condition on the non-decreasing. I have the, this is, sorry, greater equals 0, and have to prove this, and this goes through very easily. So this is something classical that is really very close to this principle. And I would like to close with two examples, two non-trivial examples where this Gerold-Kauers method worked. So one is this Turan inequality modified. So here we have, if this absolute value of x would not be here, we would have the Turan determinant that we saw before. And for this now, we have Gegenbauer polynomials. This is a generalization of the Legendre. So Legendre corresponds to the case lambda equal 1/2. They are normalized to be 1 at 1. And for this range of parameters for the lambda, we can show this inequality. And here you see, now we see really this, and this is not this determinant, but this is normalized by 1 minus x squared divided. And what we see here would be like the thing for the usual Turan inequality, the corresponding normalized expression. And this is something that, so this result is you plug it in, as I showed before, in the sum cracker, and it runs through and it's proven immediately. So this is something that is not a problem for this algorithm. If I go now to the non-symmetric case, so this is the next generalization of Legendre and Gegenbauer. They are part of Jacobi polynomials, so they are orthogonal with respect to this inner product. So here we have a weight function. If alpha and beta are equal to 0, then we are back to the Legendre case. And for these Jacobi polynomials, they are now non-symmetric. It seems that the inequality holds in this range of parameters, but we cannot prove it. We have a partial result that is similar to what the first part of the proof of Segel. So we have something like this quadratic form, something that can be easily shown using CAD in the end again, because we just have, we just need to show something polynomial is greater equal 0. And also some particular results for that indicate that this range of parameters is correct using with the help of CAD and symbolic computation. But if you are interested in problems of this flavor, this, as far as I know, is still open to prove. And the last thing that I show is actually the first thing that got me into these inequality things. This was this sum. It popped up in some application in numerical mathematics that I will not talk about now. And there exists a generalized version of this with Jacobi polynomials with alpha equal beta, so really Gegenbauer polynomials. And it was conjectured that this sum is greater equal 0. And as I said before, for holonomic sequences, for sums, we have disclosure properties and algorithms. So this whole thing satisfies a linear recurrence. So this would be of the type that we can apply Gerold-Kauers in principle, but in practice, it doesn't just work like this. But one can decompose this sum into two parts, whereas the first one, the G, it looks very simple in the form that the expression that seems to take all the oscillations of the whole thing. And the second part is still a sum, but it looks so nice and smooth. So the hope was that this is a good way to proceed, and it turned out it was, because this first thing can be, this sum thing can be estimated from below by something that is still very smooth, that is sufficient, and is of a similar simple form as the G. And this is something that then goes through again rather quickly. So in the initial run, it was like 1 hour on a laptop or something like this, which is nothing really. And the input for this stuff, for the CAD computation in the generic case, looked like this. So this is why the CAD has to fight a bit. It has higher polynomial degrees that accumulate. It has a lot of variables, which is all not so nice, but it also has some simple conditions here that are always simple. And that's all I wanted to tell. Thank you.
Thank you.
Thank you.
Questions?
Great. So maybe I was thinking that now I've seen like other methods to decide positivity of functions. There are many. There are these. I mean, SOC, no, sums of squares, and then there is the song polynomials. There are some other methods to decide positivity. Maybe you could try. I don't know how much of this is implemented, but maybe one can try to improve the CAD part of the implementation.
Yeah, so one thing is, one approach would be to really try something like sum of squares, which of course does not have to exist for things like this if you show, but to do this assisted. And there are some results by Young J. Cha. He was trying to find solutions of recurrences in terms of sums of squares or linear combinations with positive coefficients. So the problem behind in part is that of course something like this need not exist, but where it exists, it's a nice type of proof because then you have a simple argument. The other thing is, yes, there there's things like this real certify also by Mohab, Safaeldin and Victor Magran, which would be nice to use in the CAD part to have also a more human readable proof. Again, one has to, this is something that we're thinking about, one has to look at because in the end for the CAD, it's not all positivity. It's so, but for some parts, maybe one, yeah, this is something to try and go for.
Nice, thank you.
Thank you.
More questions? All right, so let's thank Veronika again. Okay.